My name is Raphael Sachs, and we're going to present today the final of the series of webinars on a digital twin solution to provide situational awareness for effective production control. I will give a quick introduction, and then I'll hand over to Tim Sing-Yung, who will explain the details. So the BIM2TWIN project as a whole fits around this conceptualization of digital twin construction. And the basic idea is that we design, we plan, and then that information is stored in a project intent information store. It's used to drive the construction through the build function. The building gets built. We monitor it using a range of technologies, collect the data, interpret the data, and compile project status information, which is then compared with the intent information to provide us insights on what we're doing and what we want to do going forward. The webinar we'll hear today focuses on the predict performance module here on the left, and we'll explain more about that as we go along. So the big idea here is to provide managers, production managers, construction managers, planners on site with an overview of the situation on the site, focusing on how the work is being done, the safety, the use of equipment, and in particular to give them an idea of how the production process might play out through to the end of the project, so as to be able to consider alternative plans and changes to the production system during the construction. The vision, the BIM2TWIN vision as a whole, is that we change construction from something that is amorphous and spread out and poorly ill-defined, I should say, to one where everyone has access to up-to-date design information, that we have real-time information about the status of the construction site and the supply chain outside of the site. All of that with the idea that we can then do informed, data-driven decision-making. And then it has the benefits that we list over here on the right-hand side. Yeah, the system architecture that we devised for the BIM2TWIN hardware and software revolves around the digital twin store, which we see here at the bottom, and we call that the digital building twin platform. Thank you. So it has an internal data model, a schema defined in a broader ontology, and it's all stored as a set of interconnected subgraphs representing the as designed, as planned, as performed, and as built states of the construction project. The information that we compile here derives from a series of monitoring systems where we have both initial data of the BIM model, the contract and schedule, and live data here at the top being collected on the site from various instruments. And the BIM2TWIN project contained 5 key work packages, each of which develop tools for these different, let's call them vertical applications that operate against the DBTP. So they have volume control, process monitoring, surface control and process monitoring, safety control, equipment optimization. And those have been the subjects of the previous webinars. Today's webinar focuses here on the production planning aspect. And as a result of that, we'll see both our local dashboard and the overall dashboard and how it's influenced by all the others. So the generic DBTP situational awareness dashboard is where people have an interface into this data store, the graph, but they are interrelated with the activities of different work packages through the BIM2TWIN project. And once again, I'll emphasize that today's webinar focuses on proactive planning and control, which we dealt with in the work package called Work Package 7. We worked in both developing and testing and validating the system on different construction sites that are listed here in 3 different countries with 3 different project partners. And this is the point perhaps to recognize all the partners in BIM2TWIN spread around Europe and Israel. They consisted of a number of universities, a number of research and technology centers, 3 construction contractors, an engineering consultancy, IT firms, both Orange and Siemens, and then Unismart and Padua University, who dealt with the technology transfer and dissemination. This has been a series of 5 webinars, and this is the 5th of that 5. And so here we are today on the webinar on production planning. And I hope that those of you who are here with us and those who will see this later on video will enjoy and learn much from the session. For today's session, we've had contributions from Flow Technologies, from SPADA, from IDP, and from Technion. We are the 4 partners who are active in Work Package 7. And with that, I hand it over to Simpson.
Thank you. So in Work Package 7, our focus is particularly in the predict performance part, and then how using the project status model and the project intent information, how we can use those to predict the performance of the construction site and use that to contribute to the project intent knowledge information. So in Work Package 7, we have 3 goals to accomplish the aim of predicting performance. So first, we want to develop what the procedures are in order to predict the outcomes of production plan and design changes. Then based on that, those system requirements, we'll build that software and then test and validate it on the pilot sites that our partners in the consortium will provide. The main goal of Work Package 7 is to enable a proactive plan, do, check, act cycle. So, and here's an illustration of what we mean by a plan, do, check, act cycle. On the left-hand side, we have a construction site where we execute our work on the physical twin. And then this information is, the progress information is being automatically collected and stored in the digital building twin platform, where we can do comparison for status against the intent. And from there, we can understand whether we need to replan and act based on our current situation. And in Work Package 7, we want to enable this cycle of where users can define alternative plans or changes that they want to make. And then we'll take this set of alternative plans, put it into the simulation engine where we predict what the fan of possible outcomes would be for each alternative. Then the users can compare between these plans and then select what would their preferred course of action be. This information is then put back into the digital twin to inform the persons on site what will be the next plan, the new plan that they should execute. And so to illustrate how the simulation provides predictive situational awareness, let's take this example where we are at decision point 1 in a project where the blue line indicates the baseline plan and the red line indicates the actual progress. And here we can see that we're lagging behind from what we originally planned. And so what the simulation can do is that we can take the original plan at this current point and say, what if we stick to our plan? What we stick to our current plan? What could be the possible outcomes of sticking to our plan? And so here we can run the simulation multiple times, considering weather variances, disruptions, and variances in the production rate, and run this multiple times until the end. We can get a fan of all the predicted potential outcomes of sticking with this plan. Now we can see here that the results are quite pessimistic. Most of the predictions are actually leaning towards that we would have a project delay, whereas very few would be on time or even finish early. So in this case, the project manager might say, I want to check what if I do some mitigation actions? What if, say, and he can come up with 2 plans in this case. So for alternative plan 1, the project manager can decide, what if we try to increase the resource, that we increase the resource utilization right now, we put in more workers, we maybe even add in an extra crane if it is extreme, and we catch up ASAP. And number 2 could be that, well, let's wait and see. Let's not try to do things too drastically right now. But we will try to ramp things up later on, where we can have much better coordination, and we're much more certain that the resources will be where it needs to be. So these are the 2 plans that the manager can come up with. And so let's run through the first plan. This could be the prediction of the first plan. And in this case, the first plan would have a high chance of catching up in the short term right here. But when we see on the tail, there's still a risk of delaying overall progress. And if we put the result of the second plan, we can see that for the second plan, there's from a global perspective, we can see that there's a very high chance that the project would finish early, and then there's a lower chance that it will have a delay compared to the first plan. Now, if we take all 3 together, bringing back what the original prediction was, if we stick with our own plan, the manager can now make an informed decision about what is the current status, what will happen if we stick to our own plan, and what will happen if we choose option 1 or option 2.
Timson, sorry, I don't know if it's me, but I cannot hear you anymore.
Yeah, me neither.
Hello?
Okay, it seems you're back.
Okay. So sorry, where did I get cut off? At which slide should I go back to, or is it just here?
I think it was here, yes.
Okay, so in this slide, I want to illustrate that now this plan to check X cycle can happen multiple times throughout the project. From decision point 1, we can go to decision point 2, where in this case we have the plan actual progress is actually ahead of schedule, and now we can actually consider whether we can slow down the pace, use less resources, save a bit of the cost, while still finishing on the milestone. And here we can have alternative plans as well. And one more thing that I would like to highlight is that this plan to check X cycle with simulation, it can happen with or without the digital twin. If we collect the data even manually, we can have this kind of plan to check X cycle. But why is it important that we have this simulation together with the digital building twin platform? It is this factor of latency. If take our original case, for example, we had our decision point 1 was right here, where there is already a huge discrepancy between the plan and the actual. And really, the first sign of delay happened much early on, maybe 2 weeks, 3 weeks, or a month in that beforehand. But in current construction sites, this process of data collection, interpretation, and then ultimately putting back to the decision maker's hand has a very large latency. And so ideally, if we can have a mitigating action happen implement our mitigation action at the first sign of delay, then it will be much more effective. That's what the digital building twin platform can offer, because with combination of automated progress monitoring and real-time interpretation and fusion of this information, we can reduce the time from signs of disruption or delay to making a decision to mitigate that delay. And so the plan to check act cycle time will be shorter because of the digital twin platform. This is the synergy between simulation and digital twin. Now, I will now go to show you how what the system we came up with in work package 7 is. So here's the overall system architecture, where we will have the digital building twin platform providing us with the latest project status and project intent. And then the user can then decide what are their scope of action and what is their degree of freedom in the plan. Once defined alternative plans and their degree of freedom, then each of the plan can go through the simulation engine, and the output will be evaluated, and we can either perform an optimization loop according to the range degree of freedom, or we can provide result directly to the recommendation dashboard where the user can compare different alternatives. And when we're talking about alternative plans, we're not so much talking just about the schedule, because the schedule is just about how we're doing it. But here we are actually talking about what are the production system parameters that, such as resources like labor, equipment, material, and also production control policy and the work breakdown structure and location system. So we're talking about parameters that the planners can change, not so much about just the sequence of activity. And let's take an example of how a plan might look like that the user can define. So for labor, we can have different work packages, such as HVAC, and for HVAC, there will be there are 3 crews here, and for one crew there could be 3 workers. The work hours per day will be 8, and they can be multi-skilled to do both ventilation and pipes. And the heat and the production rates for ventilation pipe is 10 meters per hour per worker, and pipe is 3 meters per hour per worker. And for each crew work package, these are the parameters that planner can decide on. And with the production control policy, the manager can decide for each of the materials that are being delivered, is the delivery method pull or push? Are the material arriving according to some specified date in the contract, or is it something that can be pulled according to what's needed on site, perhaps even with a buffer? And the manager can also decide that, can also specify how the site managers are actually doing the assignment of the work on site. Are they prioritizing closing off the floor so then they can hand in the whole floor to another work package? Or are they prioritize closing off by the zone, sometimes by the apartment or by the room? If that's the unit of control, say attack production. And they can also prioritize the work either by the work quantity or maybe by how much the work quantity. So, and of course, there's also considering of constraints before releasing a task to the crew, whether you're considering if the materials are available, or if the space is available. Space constraint, use of clashing or not, the material would impact the making process and efficiency, thus affecting the production rate And for location system, manager can decide what is the resolution that he or she would divide their location system by. Is it by the room, by the apartment? Is it by the floor, or even by sections of the building? In this case, it is by the apartment. Now, in our simulation, we use the agent-based simulation method, which is where we are modeling a complex system by defining individual agents or actors that interact with each other. So an agent could be people, it could be it could be the site manager, the worker, or it could be passive agents like block of concrete or a room. And so these agents will interact with the environment and then develop emergent behaviors with and so there's a synergy between agent-based simulation and the way that we have modeled our digital twin platform, because we have used a graph-based object-oriented way of describing a construction site. So we're able to so by defining agent classes, we can match the agent classes with ontology that we define in the digital building platform, and thus creating parallel digital twin and our simulation. So in our simulation, we have modeled 5 categories of agents. We have modeled DC management, which is a combination of the roles of the site manager and also the procurement department. And we have the subcontractors who are responsible for the work crews. And then we have the work crews here, which is really the core of the construction site where they perform work. We have the supplier and the design firm, which would deliver either materials, components, or in this case, information. So to get to come up with this model, the first step that we did was that we interviewed different persons on the construction site, workers, foremen, managers, and even suppliers, so that we can model this behavior of each of these agents. And so here is an example on the right where this is the example of the work crew, where work crew would first, once it receives an assignment, will check whether there's material. If there is material, then it will check whether the space, whether someone else is occupying. If it is not occupied, then they can go to it. And once we have all these behavior trees done with each of these agent classes, then we modeled it inside the simulation software called AnyLogic. And then so here, each agent has 4 main parts. First part is the parameters or characteristics that are defined from either the digital twin or from the input information that the planner had got. And then there are perception variables, where this is really the brain of this agent. This is their memory, and this is the memory of what they have done, what they needed to do, and also where they're at currently. And then there are behavior functions, where we call the specific logics, the specific logics for their action. And then finally, all these parameters are used the behavior tree on the right-hand side, where this is where the agent can decide what is the next course of action, depending on where it is at in time and in space. Now, so continuing with this part about the synergy with the digital twin. Big part that we felt was very important is that the simulation model has to be able to take the latest, the most up-to-date status, actual, that of the current day, and then initiate a model that starts at that current date, instead of having to always start at time equals 0. Because we believe that it is only when we can take the current status that we can have the best prediction of the future and avoiding a garbage in, garbage out situation. So this is how we are able to do this. On the left-hand side, we have several sources of information. We have the digital twin platform that provides us target status. We have these agent templates where in AnyLogic we've defined for each type of agent, what is their default behavior and what are the toggles that they can switch on and off based on the status. And then we have the user input module where it gives us what each alternative plan would be and then adjusting the toggles on the process based on that. Finally, we have a historical database that can be used to calibrate what are the production rates, what are the rates of destruction. And all this information is fed into a parametric generation algorithm that will take project status, take the agents, and generate in each simulation one, what is the state of every task, what's the state of every zone, and what are the states of all the agents, what are their parameters, and what have they already done, and what will they do. And then each of these simulation runs will be ran for that current state. And this is a quick visualization of one simulation, one alternative plan running starting from time 0. And we have the plan baseline here, and each of the lines here are single simulation. And here you can see this span of distribution from the earliest to the latest, and then the darker it is, the more likely the chances are that the path will be. And this is another illustration of how we took a historical project in Finland, and we're able to take the status information that is stored in the digital twin and initiating a simulation run at different points of actual progress in the simulation, predicting for until next decision interval. And here it is for 7 weeks. 7 to 7 weeks. We've published a demo version of this input interface simulation engine on our website in the BIM2TWIN. So it's BIM2TWIN.eu simulation engine/demo. And you can also use the link here. And in this demo, we took the Postialcro pilot project from Fira, and in this one you can change and define the different crew parameters and also the production control policy, and then run the simulation for one time to see how it would look, starting from either any day within 0 to 180 days, and how that simulation goes for the plan that you. We also have a recommendation dashboard that we have developed jointly with SiteDrive from Flow Technology, where we can take a set of alternative plans and compare the result between them for their schedule, for their production flow, cash flow, resource utilization, and what is the risk and uncertainty. And you can also check this recommendation dashboard out for yourself with the QR code. Now, to close this thing all up, we once the plan has been selected as the new plan, then we'll need to put it back in the digital twin platform. And this is the part where we've done quite a lot of close collaboration with Work Package 2 in the BIM2TWIN project with Orange where we can pick, where they have developed a way to store all this information as a huge graph in Orange's Fingian platform. And then we're able to use API calls to first receive what is the current latest plan. And then once the user has decided what the new plan would be, we can then use the API to rewrite that plan, upload a new plan to the Fingian platform, the graph, and set that as the new baseline.
All right. Thank you, Timothy, thanks for a very effective explanation of how the system works in a very short time. I hope that's clear for us to do it. We want to just sum up some of the lessons we've learned, both in preparing the predictive simulation and the evaluation of the alternative plans, but also in the project more generally.
I'm sorry, Raphael, but the sound is very bad. I am almost unable to understand what you are saying. At the beginning, the sound was very good. Then,
Yes.
I think, oh yes, maybe it's back.
Is this any better?
Yeah. Much more better. Thanks.
Okay, thanks, Bruno. Apologies. So we want to talk a little about the lessons learned through implementation of the predictive simulation and the evaluation of alternative plans. But we also want to look back on the learning from the BIM2TWIN project as a whole as we come to its end. So the first thing that we've found is that simulation is an effective tool for predicting project progress in short-term planning intervals. We made the decision very early on not to use a standard critical path method to plan out or to predict how projects would carry through. And that was based on the very firm understanding, I think, from a very broad body of literature, which tells us that CPM is very limited and constrained in its ability to account for all of the flows that occur in a construction site, and certainly for its inability to consider all of the different constraints. And so by using agent-based simulation, we're able to much more closely mimic how crews interact, how crews work, how the construction site plays out day to day when considering uncertainties and stochastic events that happen and the variations that are ever present. Our validations for the simulation were conducted against actual project records from 2 different projects. And we find that although those projects had a baseline plan, we also had, thanks to our partners at FIRA and at Flow OI, we have the actual records of what happened, derived both from monitoring and from time-lapse photography. And we were able to validate, I ought to say calibrate, but we were able to validate that our simulations working through different intervals were in the region of 70 to 80% accurate in terms of predicting how the actual work would, how the outcomes would be. And we feel that that's pretty good in terms of giving people an idea over the short term of what the trends are going to be. The second thing is that the digital building twin platform implemented in the graph, as was done by Orange in the Fingian platform, is highly suitable for providing the situational awareness. And that's because the dashboard was able to provide our users, our experimental users, with a very good understanding of what was going on the construction site and off the construction site. Automated processing of the raw data to project status information is really key to reducing the latency that Timson referred to at the beginning of our webinar this morning. we have not, in the broad context of BIM2TWIN, we have not solved all the problems of interpreting and processing the raw data. But our demonstrations against the other work packages in terms of monitoring volume objects like columns and beams and other things on construction site, and our ability to determine whether they are in progress, whether they've been built, whether they've been completed, or whether they've not been started. And indeed, within, for example, concrete columns, whether they are at the state of formwork or rebar or completion of pouring of concrete, that has proved to be possible. And likewise for other interior activities. We don't yet have all of the software in place to interpret what's happening in respect of monitoring the workers themselves. We have got tools now for considering safety, for planning for safer activities, but we're not yet able to map the worker inputs onto the progress monitoring in order to get productivity and other indicators, and that remains to be done. I think that we have established very well through developing the ontology, both for building product and for building process, that graph representations in the cloud are effective, they're feasible, the response times are much faster than we expected, and that can be done on an object level rather than at a file level, which has been the case up to now. And finally, in the validations that we conducted in the experimental sites, on construction sites with people working in construction, through presenting to them how the system operates, showing it how what the implications are for their own projects, and then conducting focus groups, we were able to confirm that the system was very likely to empower them to optimize their system's performance. And we often got the response that, you know, when will this be available? When can I start using it? So we feel reasonably confident that a decision support interface of the kind that Thompson showed us, using the data directly from the graph in the cloud, would be able to help people understand what the impact of their production system decisions would be on the outcomes of their projects. And finally, we'll skip to our last slide and say this, that there is, of course, as any research project ends, there are future research to be done, but we've been able to pinpoint, I think, the issues that need to be tackled going forward for commercial implementations. And that is, firstly, that a digital approach requires data to be structured and coordinated. So collecting raw data on site is possible, but that needs to be structured, interpreted at the level of raw data to information, but then it also needs to be merged with various streams of raw data in order to get the information and the knowledge that we require to truly assess what the situational awareness is. The technologies we used for data collection are becoming far more mature. Not only that, the algorithms for translating raw data into meaningful information about building objects and building processes is evolving very quickly. It's way ahead now than it was 4 years ago when we began. But there are a few points where we still need to consider, as researchers, how these problems will be solved. The design to execution transfer, where we go from project intent models to the actual construction site, that is something we haven't dealt with very much. The deployment of digital operating twins on the other end is a question. How do we go from digital construction to digital operation and maintenance, and what information needs to be handed over? Issues around safety of workers and equipment we have dealt with in terms of the digital twin. There are tools and abilities in place, but they seem to be not quite as coalesced as all the rest of the systems. And finally, there is a lot of development work to be done before we see off-the-shelf digital twin offerings where service providers can provide software as a service to, in fact, run the production control operations on a construction site. So But on the other hand, we are aware that the business opportunities there are tremendous. So we thank you for your attention, and we hope you have enjoyed the webinar, whether you're hearing it now today with us or you will hear it at some point online. Thank you very much, and we're open to questions.
Thank you. And yeah, if you have any question, please feel free to ask them or to write them in the chat or to write them to me. I actually had received one, which was more a sort of confirmation regarding the fact that currently construction companies do not have any sort of tool that is like the production planning tool. Sorry, this was the question.
Ilaria, could you frame that once more?
Yeah, sure. If like the production planning tool, it's something completely new for construction companies, or if there is something that is already being implemented, although in a different or imperfect, not perfect manner yet.
Okay, sure. That's a great question. I think we can answer that fairly clearly. Production planning happens both before construction begins, but then it also happens during construction. And that happens in various cycles of time that get shorter and shorter as the degree of planning resolution gets finer. So we begin with an overall master plan. We then use a look-ahead planning, and finally we use, in most sites, we use weekly work planning. But the tools for doing that vary. So there are, at the master planning level, all sorts of construction planning software. Most of them, almost exclusively, use the critical path method. But there are some that are less computer-based, but more based on social processes where teams get together and do reverse phase scheduling using sticky notes. And sometimes they can use software that is designed specifically for that level of planning that's online. Things like Visilean and SiteDrive spring to mind. But then as we get further into the detail of it, the ability of people to use critical path method degrades because the models are not updated, so that the systems don't have the current situation entirely updated. And that's where this latency and the cost comes in. So if you want to use critical path planning, you can do that. It's not ideal, but it is expensive and time-consuming to collect the situational awareness information and put that in before you can even run a simulation. The key thing with, and of course you have the alternative, which is more effective at a shorter time frame, which is to use systems like the Last Planner system, where again, it's a social exercise where planners get together, usually on site, and plan the next week, where the situational awareness is drawn from the collective knowledge of the group, of the team. What we think the role of the digital twin construction will be at that point is that, number one, the collection of information is automated, should be much cheaper, and should be far more comprehensive, because it's bringing together information from all over the site at fine-grained levels of detail, but also from off the site, from supply chains, from suppliers, from fabricators, and so on. So that situational awareness should also be delivered to everybody on site and off site. So that's contribution number one. And the second contribution is that we believe that our ability using agent-based simulation to analyze what the outcomes might be of different production system changes is far more accurate than people's intuition. And I think we've been able to show that in the demonstrations we've done and the tests we've done with construction planners, that they see a way to actually forecast into the future, even if it's 3 days or a week or 2 weeks ahead, which is analytically more rigorous and computationally can accommodate far more combinations of opportunities. So that's the second opportunity. And the third one, which we have not really tackled yet, is the ability to run optimizations. And that's something we're now tackling in follow-on research. So I hope that answers the question.
Thank you very much. If there are other questions, please feel free to write them. I will just remind you that, as I said at the beginning, you can find all the webinars recordings on our YouTube channel, and also we'll deliver by the end of this month a white paper on lessons learned via the BIM2TWIN project. Therefore, that will also be a very useful document if you're interested, and you'll find it published on our website. So give it a look. And I would say, since there are no more questions, that we can close here the webinar. Thank you very much to our speakers and to all of you for attending. Have a good day.
Thank you.
Thank you.
Thank you very much, everyone.